All right. Good morning, afternoon, or evening, everybody. Welcome to the CSDA Vendor Focus Tomorrow I/O NASA Commercial Satellite Data Acquisition Program webinar. This is your host, Jennifer Brennan. It's 2 p.m. Eastern Standard Time, so we're going to go ahead and get started here. I will begin today's webinar with just a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat located on the right side of your screen. If you don't see the Q&A panel, you can click on the three dots at the bottom of your screen to pull up your panel options. And then you add a check mark next to the Q&A panel. A quick word about the chat. Participants will have the capability to chat with the hosts and presenters, but not with all participants. So again, if you have any questions, what we'd like for you to do is enter those into the Q&A panel on the right side of your screen rather than the chat. Today's webinar is being recorded. The recording will be made available online within a week of completion. Once completed, what I'll do on my end is I'm going to send an email to all registrants and participants that includes links to both the recording and presentation slide decks that are used within today's webinar. As far as timing is concerned, today's event will be 1 hour and 15 minutes long with 45 to 50 minutes allocated to the presentations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During this afternoon's webinar event, we have one speaker from NASA CSDA program and two speakers from program vendor Tomorrow I/O. Now, I'm going to advance to the next slide here. Our first speaker this afternoon is Dana Ostrenga. Dana is the CSDA project manager here at Goddard Space Flight Center. She will begin this afternoon's webinar with an introduction to NASA's CSDA program and its objectives, and will then provide a high-level overview of the CSDA program vendor Tomorrow I/O, its IDIQ contract, and data access. Once finished, we will transition to our vendor speakers for this afternoon. Our first speaker is Les Lardy. Les is the Director of Business Development for North America Government at Tomorrow I/O. He will kick us off with an introduction to Tomorrow I/O, its history, and Gen 1 Constellation on-orbit assets. From there, we will transition to our second vendor speaker, Dr. Joe Monchak. Joe is the principal for Atmospheric Data Sciences at Tomorrow I/O. He will dive into a comprehensive overview of the NextGen satellite weather datasets available through NASA's CSDA program, discuss applications for their radar and microwave sounder data, and provide information about how to access Tomorrow I/O data through the CSDA program, and then finally, wrap us out with an introduction to the Gen 2 Constellation. Once finished, Joe will toss it back over to me for the final optional polls, and then from there, we will open up the question and answer session. With that comment, during today's Q&A session, we do have two additional Tomorrow I/O panelists, Clayton Bjorland and Ethan Nelson. So before I toss it over to Dana, I'd like to say a few words about this afternoon's Q&A session. We will try to answer all questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. With that, it is my pleasure to introduce today's first speaker, Dana Ostrenga. And Dana, did you want me to drive or would you like me to stop sharing at this point?
I'll go ahead and drive.
Sounds good. I sure can.
Fantastic. So welcome again, everyone, to our vendor series today for Tomorrow I/O. Once again, I'm Dana Ostrenga. I am the CSDA project manager. I'm located at Goddard Space Flight Center. And our program manager for CSDA at headquarters is Melissa Martin. So we'll dive right in. So NASA has a strong history with Earth observation data, acquiring the data, enhancing it, utilizing it, and stewarding that data. NASA really wanted to explore the possibilities of acquiring and integrating commercial data with our agency partners to support research and application initiatives here at NASA. With the increasing numbers in commercial Earth observing constellations, they leverage newer technology, providing higher spatial resolution, shorter revisit rates, and tasking capabilities, which is really unique. It makes it ideal to incorporate their data into our ecosystem and augment our existing government satellite data. So if you've missed any of our previous webinars, just to give you a little bit of background about the CSDA program, the program serves as the central mechanism at NASA for identifying, evaluating, and acquiring commercial satellite data that supports NASA's Earth science research and application goals. The program has 5 main goals. One is to establish a continuous and repeatable process to on-ramp new commercial data vendors, and I'll talk more about that in a little bit. We want to enable sustained use of that data for broader dissemination to our scientific community and all of our stakeholders. We want to ensure a long-term data preservation process, access and distribution of that data, ensuring scientific reproducibility. We want to collaborate and partner with our interagency and international partners on the evaluation and scientific use of that data. And then we want to comply, of course, with the 2003 U.S. Commercial Remote Sensing Policy. You can go to our CSDA YouTube channel to see our kickoff webinar to learn more about the program, and you can see all of a list of all of our commercial partner webinars to date. So this slide just kind of showcases our diverse array of commercial vendors, each providing unique satellite data products to help NASA advance Earth science. We currently have 15 commercial vendors on contract that we can acquire data from. For multispectral imagery, we partner with Maxar, BlackSky, and Catalogue, where Planet operates in both the multispectral and hyperspectral domains, alongside Teledyne Brown Engineering and Pixel, who specialize in hyperspectral data. Another one of our vendors, Airbus, operates in both multispectral and the area of synthetic aperture radar, alongside our SAR providers, which includes MDA, Umbra, ISI, and Capella Space, that all enable weather day-night imaging. For monitoring methane emissions, we go to our provider, GHD-SAT. For GNSS radio occultation capabilities, they come from Planet IQ and Spire, contributing to those valuable atmospheric profiles. Digital elevation models are sourced from Maxar and Airbus. And for precipitation data, we utilize data from Tomorrow I/O, who we are here to hear from today. Together, these vendors enable NASA to access high-value commercial satellite data across a broad range of Earth science applications, enhancing our ability to monitor and understand our planet. When NASA evaluates commercial data, which is a big part of our program, it really provides confidence not only for our science community, but also for our commercial partners themselves. So I just want to highlight some of those benefits. There's our partners gain greater recognition within the science and application communities. Being evaluated by NASA and our interagency partners really signals a credibility alongside our federal programs. Second, it builds trust. So with customers, investors, and partners on their side, it just shows that the data meets rigorous NASA standards. Our commercial partners also gain access to NASA's deep expertise in data quality, which can strengthen their products and practices. And then these evaluations, they often strengthen the commercial partner capabilities we have a feedback and share all of our information from our evaluations with them. Through CSDA communications, our commercial partners also see increased brand awareness and visibility across the research ecosystem, partly contributed today by the webinars that we're hosting. And finally, NASA evaluations, they bring greater exposure to the full utility of the data alongside the communication of research initiatives from our commercial vendors, ensuring that it's used to its maximum potential. So really, in short, NASA's evaluation process not only assures the scientific community of data quality, it also directly strengthens commercial partners' credibility, capabilities, and visibility in the marketplace and the federal space as well. Since that evaluation process plays such a critical role in our program, I just want to walk you quickly through the data evaluation criteria that is part of the process when assessing the quality and utility of the data. So we really look at how easy it is for researchers to search, discover, and download the data from our commercial partner systems. If access is difficult, it really limits the scientific use. Second, we evaluate the completeness and accuracy of metadata. Good metadata provides the context scientists need to properly interpret and apply the data. Third, we assess vendor support services, whether their responsiveness, availability, and technical expertise. So that strong support helps researchers resolve issues really quickly when they try to integrate the data into their research and applications. And then fourth, we consider the usefulness of the data for advancing Earth science. Does it align with NASA science objectives and help fill some important gaps? And finally, we evaluate the quality of the data itself. Things like geolocation accuracy, radiometric accuracy, and calibration using ESA NASA evaluation guidelines. So together with these criteria, ensuring that NASA brings in commercial data, it's not only high quality, but also accessible, well-supported, and really able to deliver real value to that science community. So since the evaluation, it's not going. Since I mentioned part of our evaluation program, I want to talk a little bit about our ESA-NASA Joint EO Mission Quality Assessment Framework. This helps feed into our evaluation process. ESA EDAP established their own EO Mission Quality Assessment Framework, and in parallel, CSDA was also creating an evaluation process. We decided to come together and develop the Joint EO Mission Quality Assessment Framework that really helps us ensure that the decisions on acquisition and commercial data are made with confidence. All of our evaluations go based on this framework, and any guidelines that aren't currently developed, NASA and ESA are partnering to develop those guidelines based on the sensor capability. So just to highlight a couple new things with the CSDA program, right now we have all new business is currently on ramp via indefinite delivery, indefinite quantity process, and we are really currently in the middle of an on-ramp period right now where we plan on bringing in new commercial partners earlier this calendar year. We're also continuing to grow our collaborations with federal partners as well as international partners. And I really want to emphasize something that just was released this week, the new CSDA data acquisition request system. It's a new exciting thing for us to help facilitate the acquisition and tasking of our current commercial partners. It's a new dashboard that lets authorized users submit and track proposals for data for CSDA's commercial partners, and it includes the ability to request tasking of a partner satellite for data that has not yet been acquired by the program. And it also really makes the ability to find out what archive data is available as well. The system is accessible through the Satellite Data Explorer interface. And then now that brings me to the CSDA Tomorrow I/O partnership. In September 2024, CSDA awarded Tomorrow I/O an IDIQ contract under our On-Ramp 1 RFP solicitation. And through this effort, we acquired Level 1C and Level 2A data from their precipitation radar for evaluation. Our CSDA subject matter experts worked to evaluate the data and better understand Tomorrow I/O's data products. And that evaluation results were briefed then to headquarters and to Tomorrow I/O in August of last year. The final subject matter expert quality assessment report will be released about the February-March timeframe, give or take some dependencies that we have. And download all the data that we have acquired will be downloaded and be prepared for release through the CSDA Satellite Data Explorer, or SDX, alongside the evaluation reports. If you qualify under one of our EULAs, you can register for access on the CSDA website. The SDX provides a central web interface for search, discovery, and distribution of all of our CSDA data, and this really ensures easier access for researchers and a smoother integration into our NASA data systems. That data that's downloaded will continue to be integrated and available through this interface, and then is also being added to the Earth Data Search client. And that previously mentioned, I just want to reiterate that previously mentioned DARS system is available also through this SDX. So that brings us to the next portion of our webinar. So please welcome again our invited speakers who will talk to you about Tomorrow I/O. And I'll stop presenting unless you can take it from here.
Absolutely. Thank you so much, Dana. Joe, if you maybe want to pull up our presentation, it's just going to be a minute. There we go. Thank you. Thank you so much, Dana. Thank you so much, Jennifer. Definitely very excited about our partnership with NASA Commercial Data Acquisition Program, and appreciate this opportunity to just tell the world a little bit about Tomorrow.io and walk through some of our capabilities. So my name is Les Lardy. I'm the Director of Business Development for North American federal government agencies. Been with Tomorrow.io a little over 2 years, and in that time, just really focused my time on building the partnership with our federal government agencies. NASA obviously is one of the most important one of them. So that's my role at Tomorrow.io. Next slide, Joe. Just going to walk through the agenda. I'm going to kick it off give a high-level introduction of Tomorrow.io and what our mission is. Then I'll turn it over to Joe Munchak. Joe is going to talk a little bit more about our Constellation, our Gen 1 Constellation, instrument specs, right? A little bit more technical details about the kinds of data that we're able to generate and pull down from our satellite constellation. And then we'll also give a very brief sneak preview of our next generation, or our Gen 2 constellation, which we've been very, very hard at work on. I'll just give a very slight preview of that. And then we'll toss it over back to you, Jennifer, for the Q&A. So next slide. So I like to, when I talk about Tomorrow.io, I'd like to give a global grounding of our mission, right? Especially this week when you have the World Economic Forum, convene again in Davos, right? So every year, the World Economic Forum, they commission a survey. And the World Economic Forum is just a collection of global leaders, right? The true movers and shakers, right? Government leaders, business leaders, NGO leaders, the real decision makers in the world. And they ask them, they perform a survey every year where they ask, what is the number one risk that faces the global economy? And last year, weather was the defining risk, according to the movers and shakers who are assembled in Davos this week, right? And next slide. And it wasn't because they weren't given a variety of options. I mean, they were given a whole variety of options, but just true to the importance of the role and the critical role weather is going to play today and in the future. They said, you know what, of all the risks that are emerging in the world, extreme weather is really the number one. Next slide. Really came ahead of things that are top of mind, like AI and societal, economic inequality and all those things that we all know about, that we think about. Weather, according to the World Economic Forum, last year was the number one risk. And that's important because, next slide, Joe. I just wanted to highlight that when we saw the results of that risk survey, it was not a surprise to us, right? It was not a surprise because 9 years ago, our co-founders really understood the importance that weather was going to play in our society. Long before where that bubbled up to the number one, on surveys, we really knew that weather was going to really dictate, how critical decisions are made across various industries, various sectors. And that was really what informed the founding of the company. We really saw this, 9, almost 10 years ago, right? So no surprises there. So that's what led to the founding of the company about 9 years ago. It's headquartered out in Boston. We have 2 additional hubs. We have a space and sensors division out in the Denver, Colorado area, where we put together a lot of our space payloads. And we also have a second hub in Tel Aviv, which houses most of our software team. We've won some really neat awards, really testament to the quality of the products and services that we've built. Private company, founded about 9 going on 10 years ago, because we really foresaw the vision and the role that weather and the management of weather was going to play in society. Next slide. So very unique in the private weather enterprise, we're fully integrated, right? And what that means is that we capture the full value chain. We're an end-to-end customer. I like to read this slide from the right going to the left, because we started out as a software company, right? Like I said, our mission initially when we were founded was to really deliver decision-making software and tools to people who made decisions, right? Operators, right? Public sector employees who are in charge of making decisions to save, property and et cetera, right? We wanted to deliver and give them the tools to be able to make really informed decisions about high impact weather events. But very quickly, we realized that the decision and the tools that we're giving to our customers was really only as good as the forecast skill, right? And so that led us to begin thinking about developing our own in-house, proprietary modeling systems, right? Because if you want to deliver a tool that will help somebody make really informed decisions about the impacts of weather, you better make sure you have your arms around forecasting and providing the most accurate or most highly skilled forecast. So then we got into building our own AI-powered modeling systems in-house. We did that a couple of years, and then naturally we realized that the skills of your forecasts are only as good as the data that feeds into them, right? So in a way, it was a natural evolution of our company, right? We began as a software. We started to do our own in-house modeling to make the software better. And then we decided to go to space to make our models better, right? And so that has really been the evolution and the story of our company. Very unique in the sense that we're completely full stack, right? From owning our own data and satellites to modeling and developing our own AI models, as well as having this really, really neat software platform that arms operators and decision makers with decision-making tools. Next slide, Joe. And just wanted to give a sense for the industries that we serve, right? We not only serve and partner with government agencies like NASA, but we serve a variety of customers across various industries and various verticals. A lot of the brand name logos you see on here rely on us for weather decision making, as well as some of our data. So just really wanted to show that we really serve a broad base of customers, not just government accounts. And with that, Joe, I think I'm going to turn it over to you to kind of dive a little bit more into our current generation Constellation and go deep in the technical, and then maybe talk a little bit, give a preview about our next generation.
Yeah, thanks, Les. It's a great pleasure to be speaking to this audience, and we really hope to educate you about the company and the products that we have available, and that'll be upcoming in the near future. So first, I'm going to talk, as Les said, about our current on-orbit constellation. This is a hybrid constellation of two types of satellites. So beginning 2 years ago, we started launching precipitation radars. One of those deorbited last year, but one is still on orbit and operational, collecting data. But more recently, we've been launching CubeSat microwave sounders. We just completed the launch of the 10th and 11th of those. And so we are filling out that constellation, which will ultimately comprise 18 or more of these microwave sounders in low Earth orbit. So what that is going to give us is global coverage on hourly timescales of at least for the microwave sounders. These are measurements that are all sky temperature and humidity profiles. It contains valuable information for precipitation, for tropical cyclone warnings. So it's collecting data of parameters that evolve rapidly, which is why we need that sub-hourly revisit rate. The radars are more of a technology demonstration, as you'll see. So they have some limitations in terms of coverage compared to the sounders, but they were very important to as a stepping stone towards our next generation radar, which will go onto that Gen 2 constellation. So that's the current status in short. And we'll go into a little more detail on these instruments. So the radar pathfinders, as we call them, were Tomorrow R1 and Tomorrow R2. As I mentioned, these were mainly to reduce the risk of some of the radar back-end technologies that eventually we were planning to put onto a more capable radar. But a lot of the back-end is identical. So what it is a single frequency Ka-band radar based on a software-defined radar. So we can do a lot of flexibility in terms of the waveforms and scan strategy on board. It's a single solid fixed reflector, like you see in this image, with a 1.2 meter diameter. So that gives you about a 5 kilometer ground footprint from our initial altitude, which was around 500 kilometers for both of these spacecraft. It's a small ESPA class, so think mini fridge sized. Not a big satellite by any means, but not a CubeSat either. And what this gives you fundamentally is a precipitation profile with 250 meter vertical resolution and pretty good sensitivity. There's also a lot of sensitivity to the surface backscatter, which tells you, depending on whether you're land over ocean, characteristics such as the ocean surface wind speed, or maybe something about the surface roughness or soil moisture over land. We also, because it is a software-defined radar, can operate it in an altimeter mode with a different transmit waveform and bandwidth, and that gives us sea surface height and significant wave height measurements. So as I mentioned, Tomorrow R1 was our first satellite, launched in 2023, deorbited at the end of last year, and that data archive is available in the CSDA program. R2 launched a few months later in a slightly higher orbit, so it has had a longer mission lifetime and is currently in extended operations, where essentially we're continuing to task for precipitation, but also doing some specialized tasks over a ground-based transceiver for active calibration and better characterization of the beam pattern and side lobes, and also this altimetry demonstration that I mentioned. And that's expected to deorbit later this year. So time is running out for Tomorrow R2, but both R1 and R2 missions were very successful and achieved all the objectives that we set out for them. This is a little more detailed technical information about the payloads on R1 and R2. So think of this as maybe a cheat sheet to look up for the radar transmit parameters, especially when we're in the precipitation mode. So I won't go through all these details, but I think the most important characteristic is the sensitivity. So in our standard precipitation mode with about a 250 meter vertical range resolution, we have about an 8 dBz sensitivity. So that's about 5 dBz lower than GPM's KU and Ka band radars. I think might be even better than the Ka band radar by a bit more than 5 dBz. So we are seeing parts of storms and lighter precipitation than GPM sees, although there is, of course, the limitation that we don't have a full wide swath scan. It is just a single beam sweeping out a curtain underneath the radar. So it's maybe more akin to the CloudSat or EarthCare missions, if you're familiar with those. So here's an example of our very first science data that we collected over precipitation. A few months after launch, after we'd done all the commissioning and software checkout, we were able to start transmitting some pulses, and we transmitted some over this very innocuous-looking band of clouds over the Western Pacific Ocean, but it did contain some shallow precipitation and even some reaching up into the mid-levels. You can see there the ecotop's got up to about 12 kilometers. And it was very exciting to see this. It has all the characteristics that we expected in terms of noise. You can see the profiles very well. There's definitely some attenuation, which you would expect that Ka band in a more intense precipitation. And just as a very quick sanity check, at the same time, we were running a real-time geostationary viz multi-channel precipitation retrieval for our platform product for nowcasting. And we compared that to what we got from the radar. And in general, the locations matched up, which validated our geolocation. But of course, you get a much more detailed profile and higher accuracy from the radar. So, it's important that we didn't expect these to match exactly. But we did see some confirmation that we weren't completely out of line with the measurements or the calibration or geolocation initially. And so, of course, we did some very extensive evaluation internally, for our own purposes before submitting the CSDA to confirm that validation. So we validated both the level 1 reflectivities as well as the level 2 precipitation products. So the reflectivity, the methodology we used was mostly the ocean surface backscatter. That provides a very consistent target. It's if you know the wind speed and the incidence angle, you can predict the ocean surface backscatter to a high degree of accuracy, and that's actually based on measurements that were taken with GPM. So what you're seeing here are biases relative to a lookup table that was derived from GPM's Ka band radar, and you can see the biases there are less than half a dB, and this was using the pre-launch measurements. I think we were able to refine them a little bit with some post-launch characterization to get even closer than this. But in any event, the calibration accuracy is well within requirements for this type of instrument. On the precipitation side, so we have a level 2 product that we'll go into more detail later, but this is actually the result of the CSDA evaluation, but we performed our own evaluation with a similar methodology and we got very similar results. In general, you can see that we see a very high correlation between the measurements that we're taking with the Pathfinders and the MRMS, which is NOAA's gridded ground radar based analysis over the United States. And we also see that good agreement out to pretty high rainfall rates. So I think we found, at least internally, that we can get up to about 70 millimeters an hour at Ka band without any bias or loss of accuracy due to attenuation, because there's a lot of information in the profile and in the path integrated attenuation that can be used to derive rainfall rates at even up to those high intense values. And all these results again were reviewed by the ESA NASA evaluation group, and they gave us either excellent or ideal ratings in just about every single category related to our documentation and retrievals, and then of course the geometric and radiometric accuracy, as well as the level 2 product accuracy. So that covers the precipitation radar. Next, I'm going to switch over to the microwave sounder. So this one is actually even closer to a NASA mission. It was derived very much from the NASA Tropics mission, so it's a very similar instrument. It's a passive microwave sounder with 12 channels from 91 to 204 gigahertz, really taking lessons learned from the Tropics mission to make some improvements in the receiver backends and calibration targets. But fundamentally, this is taking wide swath measurements that are relevant to temperature and water vapor and precipitation. So this is what the satellite looks like. So it is a little bit larger than Tropics. We went from a 3U to a 6U bus, and let us put in a additional calibration target on board that complements the noise diodes that were used with Tropics. We also switched out the receiver backends for the temperature sounding channels near 118 gigahertz. So these are now measured with a digital spectrometer that gives us some benefit in terms of repeatability from instrument to instrument. I think Tropics had some issues with crosstalk between channels there that have been completely eliminated with this new design. And so we're finding that those measurements and those channels are very stable and high performing with TMS. So as I mentioned early on, we had just completed the launch of our 10th and 11th satellites, and this is our current operational status. So we're collecting data from 10 out of the 11 that we've launched. A few of the early ones had some issues due to the use of refurbished components, but we've been able to recover and come up with alternate modes of operating some of those so that we can continue to get science data. And what that's giving us right now is just about a 1 hour revisit rate with the satellites we have currently on orbit, and we plan to continue to launch these, like I said, in the first batch, which we call TMS 1.1. We're building 17 of these, and launches are scheduled to complete there early next year. And then we'll move on to a minor upgrade before we go to the Gen 2. We're going to have a 1.2 refresh with an additional dozen or so satellites. The instrument itself, this is the detailed spec sheet similar to what we had for the radar. It's essentially the same antenna as Tropics, so we have a very similar beam width and spatial resolution and scan pattern. Like I said, the main differences are in the receiver backend. So the 118 gigahertz channels are now dual sideband. I think the 91 gigahertz channel went to a single sideband, which I think whereas it had a dual sideband on Tropics, but otherwise very, very similar, especially at the G-band channels. I'm posting some of the average NADT numbers. Those do vary a bit from satellite to satellite, but that's generally, you think about plus or minus a tenth of a Kelvin from these. And those are the weighting functions on the right that those channels give you, with the temperature sounding channels on the left and then the water vapor sounding channels on the right. And this is for a typical atmosphere. There will be some variation, especially in the water vapor channels, because those are dependent on the actual concentration of the absorber in the atmosphere. So what does the Constellation give us in terms of temporal performance? This is one of the key reasons, after all, that we launched this many satellites. So if you look at what the current state of government-operated microwave imagers and sounders, and this is an example of what's the GPM project uses. I just took this snapshot earlier this week. You can see that there are just a handful of sensors out there, and there is some change going on in this Constellation. So the MHS and SSMIS are aging out, and will probably mostly be decommissioned in the next year or two. and they're being replaced by newer sensors like the Arctic Weather Satellite or the METOP-SG, MWS, and their own microwave imagers. So there will be some change in the makeup of this, but the overall quantity of instruments is going to be mostly the same. What this gives you on an hourly basis is about 45 to 50% coverage of the globe, as you can see on that top image. When you add in the TMS constellation, and we're to just take what the most recent available observation is at any given time, we're now finding that TMS is providing the most recent observation over the vast majority of the globe, just by virtue of being in different orbits and having this distributed ground station network where we're getting an average latency of about 30 to 40 minutes. And you can see there when you add TMS in, the difference is visually apparent. We're now up to about 70 to 80% coverage in any given hour when you combine the government-operated satellites with TMS. And so we expect those gaps to continue to shrink as we continue to build out the constellation, but already hourly observations at some of these frequencies are a reality. Okay, so this is another way of looking at that data. I think these are 3 hourly snapshots before we had our most recent launch. So some of these gaps are already getting better, and it just shows the background infrared mosaic on, and then you have the TMS swaths at 91 gigahertz on top of that, showing that we are penetrating through some of those thick clouds and seeing the core precipitation and water vapor patterns that you can't get from the geostationary alone. And we've also had a lot of evaluations, and in this case, not from NASA, but from JCSDA and NOAA and NOAA's partner institutions, as they've been evaluating this data. And JCSDA performed an observing system experiment from our first 4 sounders over a 6-month period, and they found significant forecast skill improvements across all the parameters, so temperature, water vapor, and even winds, which aren't directly measured, but in a data assimilation system, you can improve the accuracy of wind analysis and forecast in 3D with the microwave sounder data. In this case, they were using the MPAS model and the JEDI data assimilation system. So that's an overview of our payloads. Now I'm going to go to some applications, starting with the radars, and I'll move on to the sounders. The radars, of course, are very good for observing precipitation. That's what they were designed to do first and foremost. So here's just some example scans through a couple of tropical cyclones that we were able to observe. And one thing I'll note here is that the Pathfinder radars are taskable. And so what that means here is that we can steer the beam to the left or right of nadir, and you can get pretty good precipitation measurements out to about 20 degrees. We tried going even further out to 30 degrees, but you really start to lose the near surface signal, and you can only really see mid and upper levels of the storm, and it becomes very blurry because of the way that the beam gets smeared at those large incidence angles. So that is a limitation of the radars, but it does mean that we aren't limited to just overpasses of what's directly underneath us. But if there's a storm of interest out maybe a few hundred kilometers away from the nadir track, we can steer the antenna to view that storm directly, and that's what we did in this case. This is all based on forecast tracks, so sometimes it works better than other times depending on the accuracy of the forecast, but we were able to get a few this way, direct center overpasses. And you can see here again the reflectivity profiles and at level 1 on top, and then the derived water content profiles in the middle, and then the precipitation rate at the surface. One of the things that we emphasize in our level 2 products is uncertainty characterization. And so every value there has some sort of uncertainty because there is inherent uncertainty in the conversion of radiances or reflectivities back into geophysical units. And so we have these quantile distributions for some of the surface parameters like precipitation, and then something more like a standard deviation for the vertical level parameters. But you can see here just kind of the dynamic range that we get from the radar and our retrieving mean precipitation rates well over 50 millimeters an hour in some of these more intense convective regions, illustrating the capability of the Ka-band radar too. I distinguished between those heavy events and lighter events, even though there is a lot of attenuation in the level 1 data. Here's another example, this time of an non-tropical storm. This was a frontal zone over, I think, the South Indian Ocean off the coast of South Africa. And this is just a really nice example of a sloping frontal region where we have this temperature gradient over the swath that's leading to a change in elevation of the bright band. And you can see the retrievals capture that very well with the ice and rain phase transition. And so this is another, just a good illustration of the type of data we have. It's also a good illustration of how the data is oversampled quite a bit, both horizontally and vertically. So I think that the ground sampling is about every 700 meters, and the vertical oversampling is at about 50 meters, even though the native vertical resolution is about 250 meters. So just have to be careful that the sampling does not equal the resolution in this case. And finally, here's an example of a very classic looking squall line, in this case, just off the coast of Australia. And one of the things I like to point out with this example is the probabilistic classification that the level 2 algorithm does. And you can see there on the bottom, we have 4 categories, but there's 3 that are relevant in this case: the probability of precipitation reaching the surface, then the probability that precipitation is convective, and finally, the probability that there's hail within the column. And these are some of the highest hail probabilities that I've seen in this particular product, and of course it corresponds with a very intense storm. So while we don't have direct validation in this case, it is showing that there is some signal in the Ka band data and profile shape, particularly the very high reflectivities at high altitudes and maybe strong gradients in the reflectivity that are indicating a high probability of hail. What we have validated is the precipitation rate, and here's some examples of comparisons to MRMS where we take the product that comes out of the level 2 algorithm and compare it to MRMS that's co-located and convolved to the same beam pattern. So it should represent the same spatial distribution. And you can see here the correlation is very high, which, for these small events, there's a lot that has to go right for this to happen. First of all, the geolocation has to be really precise, or else slight misplacement would result in a bad correlation, even if it's getting the magnitude right. And then of course you actually have to get the magnitude right, and that's showing here in this range up to about 15 millimeters an hour. We're getting a very good match to the MRMS magnitudes. Here's another case over the southeast U.S. where we had a very complex system with some convection over Florida and then some more stratiform rain over Georgia, over a wide area. So this is one of our key validation cases just due to the amount of precipitation that we observed. And you can see again, both the convective area and that more stratiform area are correlating very well with MRMS. And finally, there's a snow event. I think this one is a good illustration of the sensitivity of the Pathfinder radars. You can see this event, is very detectable, very close to that detection limit around 8 dBz. And we're seeing the very light snowfall rates of a millimeter per hour or less, but they are being picked up by this radar, and the shallow profiles are not a problem for the near-nadir Pathfinder scan in this case. So moving on to the microwave sounders, there's quite a bit you can do with them. I'll start with the precipitation example, since that was one of the key reasons we launched them, was to improve global precipitation estimates and nowcasts in real time and out to 3 hours. And we had to develop some new techniques to do this. So there's a lot that goes into this slide, and I'd encourage you to read this publication. It actually was just, I think it's accepted now in Journal of Hydrometeorology. So there should be an updated DOI for that after we send in the revisions. But the basic premise is that a microwave sound overpass has information, first of all, that gives you better precipitation retrievals above what you can get from just the geostationary visible and infrared data at that time. And that's not a surprise. There's more information content in precipitation at microwave frequencies and in visible infrared, even though the VIS-IR is at much higher spatial resolution. I think the important finding of this is that we can maintain some benefit of that information even for about an hour or 70 minutes after the overpass. And so as long as our latency is low enough and we're getting new overpasses on this hourly basis, we're adding skill constantly to the geostationary data, even if we don't have maybe an overpass right at a particular time, because with the Leo constellation, that'll never be the case. We also found a lot of applications towards tropical cyclones with this data, and this came out of a partnership with the NOAA evaluation, and they sent the data to the Sims Cooperative Institute at the University of Wisconsin, and they were able to feed our data right into their DMINT 183 algorithm, which had been developed for tropics and some other sensors, and found that first of all, the intensity estimates lined up very well with what they were getting from the other sensors, and also filling a lot of gaps, especially as I mentioned now that some of those legacy sensors are aging out, and these coverage gaps are increasing, and there needs to be something to fill the place, especially for storms that change intensity rapidly. And so here's just some more examples of tropical cyclone observations that we took from TMS last year. On the left is one of our overpasses of Typhoon Regasa, which was a very intense storm that had a very strong warm core anomaly, which is something that I think is a really unique feature of these 118 gigahertz channels, that we can see this anomaly at the high spatial resolution from a CubeSat. So our footprints at that temperature sounding channel are about 24 kilometers, which is smaller than a footprint than the temperature sounding channels from ATMS, or certainly the AMSU A sounders at 50 gigahertz. So we can actually get better resolution from a CubeSat than you can from a larger satellite by going to these higher frequencies. And there is some more contamination from the precipitation, although in channel 7 and 8, we're actually seeing above the precipitation entirely. And so you don't see any of those artifacts. And even channel 6, that they're fairly minimal. So there is definitely benefits to having these channels at this high resolution for tropical cyclone intensity monitoring. And then on the right, I'm just showing some examples of cases where we had a lot of overpasses just by the nature of the constellation and how the orbits aligned with each other on any particular day. That show you what 30 to 60 minute refresh looks like for microwave data in a tropical storm. And we also had many overpasses of Hurricane Melissa as well in the Caribbean as it was growing and striking Jamaica. That was a very, very intense record-setting storm. So another key application of the TMS data is for numerical weather prediction. And so we've run our own observing system experiments in parallel with the effort that JCSDA was doing. And this these results essentially used, again, JEDI, but with a UFS, in this case, forecast model. And they actually were just accepted to QJRMS. So there is a new DOI for this paper as well. But the results there, in a nutshell, showed that two TMSs had an equivalent impact to two ATMSs, in this case, NOAA 20 and 21 for water vapor, and about half the impact for temperature, which is in line with expectations, and given the difference in noise in TMS versus ATMS. So we're getting very high quality information and high impacts, and you can extrapolate those results out now to the full constellation that we have, and you can imagine that there's probably even stronger impacts. But by just having a lot of sensors out there in data sparse regions. So moving on to the data catalog now, and this is going to cover the holdings that are both in CSDA and ones that are not yet, but we hope to onboard at some point in the near future. So all the sounder data products currently are not available through CSDA, but we do have quite a few, and again, we're hoping to onboard these. Some of these are available through the NOAA commercial weather data pilot, but their distribution is more at the institutional level than to individuals. But those include level 1B and level 1C products. We also have a level 2A product that right now is just being used internally. But I'll show some examples of that. That gives you temperature and humidity profiles and some integrated cloud properties. We are currently working on a precipitation product with some using some machine learning methods to do resolution enhancements. And then we also have a gridded level 3 product that is more for the constellation on a global lat-long grid in the ZAR format. So it's a very cloud-friendly format for doing global analysis from essentially the level 1 data. The radar data products, which are in the CSDA catalog, include the level 1 GeoProf. That's just a calibrated reflectivity profile along with a lot of ancillary data. And then our level 2, a preset product, which I've shown some examples of already, but we'll go into a little more detail. We also have in development this level 2 altimeter product that will give the surface elevation and significant wave height. That's currently experimental and not yet available in the CSDA program. And then finally, internally, we have available to our enterprise customers the unified precipitation, which is a multi-satellite blend for real-time and nowcast, which is what I was showing in that early example of the TMS application, where you blend the geostationary and TMS and other microwave sensors that are available with low latency. So I'm going to go a little more detail on the radar products here. This is the Level 1C GeoProf algorithm. And essentially it gives, again, the calibrated reflectivity profile, but also a lot of additional ancillary data. Of course, it performs a geolocation. One of the things that is included in the file is the range weighting function of the particular transmit waveform that we had, which is helpful for subtracting out the surface return from the precipitation echo and being able to distinguish those. So that's included there as well. We also do a lot of convolutions of that beam with the a DEM and water land masks, so that we have that did a lot of help. That was very helpful for geolocation validation internally, but also can be helpful for some of those precipitation products down the line. And the precipitation product flow looks like this. So there's additional geolocation step there in a preprocessor that identifies the precipitation echoes. Then we perform a surface reference technique, very similar to how the GPM radar algorithms do it, to derive a few different estimates of the path integrated attenuation with different reference sources. And those all go into a solver. In this case, we're using a neural network to solve it, and it's based on the DPR, the GPM DPR profile. So in a nutshell, what we're doing is we're taking profiles that were derived from combined KU and KA band data and then use only the KA band as the inputs. So we're trying to emulate this dual frequency retrieval, but just using a single frequency as the input. So of course you lose some information there, but rather than having to prescribe a lot of relationships between things like the profile shape or the drop size distribution, that comes out naturally from these profiles that were derived from the dual frequency radar. So we're trying to retain as much of the accuracy as we can. And I think that's part of the reason why we can retrieve some of these higher precipitation rates. But we also get the mean particle size profile. Again, you've seen the water content profile and phase, and then this probabilistic classification that comes out of it. For the microwave sounders, we do, again, a suite of level 1 and level 2 products. Here's just an example of level 1 brightness temperatures and a level 2 multi-property retrieval, again, with temperature and humidity profiles, and then 4 parameters related to precipitation: the ice water path, liquid water path, the surface precipitation rate, and then the storm top height are all parameters that come out of the microwave sounder data, and that can be retrieved with some fidelity. And we're also innovating on this algorithm. This is a quick preview of just some recent work we've been doing to use more 3D machine learning methods to retrieve these properties, and that's going to allow us, I think, to get better data in a lot of different ways, take advantage of relationships between pixels maybe inside a storm and the nearby environment, and reduce some noise in heterogeneous regions optimally, and we can see that already in some of these quick previews that we're doing. So this is, I think, an extratropical transition of Hurricane Erin that happened over the summer, and it just had a very very classic textbook structure of an occluding cyclone there, and you can see the storm top height on the left and the specific humidity at mid levels, and then upper level temperatures, which show that warm core still being carried into the extratropics with the storm without any artifacts from scattering, in this case from the precipitation at this level. So we're really seeing the benefits of these 3D methods here. So there's more to come on that. But if you're interested in the data, particularly the data that's available in the CSDA program, it's a relatively simple process to sign up. And, there are some parameters in the ELA that need to be adhered to get approval. But once approved, you should be able to access the data. And to find the Tomorrow I/O data, I would recommend just quickly filtering for precipitation radar, because it is the only precipitation radar instrument in the catalog currently. And are happy to assist in any way. But I think the CSDA program also has quite a bit of support options that we've listed below there as well. So last part of my talk is just a very quick preview of what's coming next that we're really excited about, and we'll be announcing this more in the near future. So if you think about the current constellation, it's about a dozen or so satellites. We plan to increase that number slightly and fill it out, but the instrument capabilities and the satellite sizes are pretty small. So or thinking like, well, what should we do next? Like knowing what we know now about going to space, building a hardware, what the user needs are. We settled on a new architecture that is much more capable than the current one. So I think now instead of just a dozen satellites, multiple dozens of satellites, not just one instrument per satellite, but a handful of instruments per satellite. One of the key ones I can say at this point is that a scanning precipitation radar that has a wider swath at Ka band is being designed and planned to be on this constellation. And then there'll be many other sensors. We're leveraging something that's repeatable and resilient. And one of the key aspects too that we found with our current constellation was trying to get the latency down. Now there's solutions for that in terms of satellite to satellite communications that can be utilized, onboard processing to get the most relevant data down quicker. And so think instead of latency being measured in tens or of minutes or in the low hour range, now we're talking seconds. From measurement being made to being received at the ground and available. So all that's going to power our platform and customers toward the end of the decade and beyond. So we're really excited to get started working on this. And again, you'll hear more about it soon. So that wraps up my portion. I think we probably have some time for the Q&A now.
We do. Thanks so much, Joe. All right, I'm going to kick it off with a question that was posed in the chat. Are there any plans to look at the 50 to 60 gigahertz oxygen band in the future?
Yes, so that is definitely in the plans for our Gen 2 constellation. We'll have a microwave sounder that will carry that band in addition to the 118 gigahertz. That was the limitation of the CubeSat. We really didn't think we could get adequate spatial resolution at that channel with the size of antenna we had, but going to a larger satellite will enable that.
Okay, thank you so much, Joe. So the next question is, does Tomorrow I/O maintain a full archive of the TMS microwave sounder measurements? If so, is it accessible? The CSDA Satellite Data Explorer page only mentions an archive from October 1st, 2023 through November 30th, 2023.
Right. So in-house, we do have the full archive of the TMS data. Right now, in terms of publicly available sets, there's a few different options. None of them cover the entire archive. So our biggest partner there has been NOAA that did their own commercial weather data pilot, and that began in February of 2025. So they have some data going back to then, although it's not every satellite. We intended to only give them data for satellites after several months of calibration, so they don't have some of that early data, although we do go back and reprocess it. So there is a uniform record going back further. That's something I think an open question for maybe future onboarding. I don't know, Les, do you have a comment?
No, I was just going to say that so microwave sounder was also one of the instruments we proposed in the last round of this commercial, the NASA CSDA on-ramp. So it's we have to go through the process, but we're hoping that, through this wonderful partnership we have with NASA CSDA, we'll in the very near future, hope to have microwave sounder archive data also through the NASA CSDA program. So more to come on that.
All right, wonderful. Thanks so much, Joe, and thanks, Les. Okay, so our next question is, it seems like a number of space vehicles are arrayed in very similar LTANs. Is your hourly refresh an average of very long and very short revisit times and less representative of revisits around 1 hour?
Yeah, so that's a great question. And the answer is that, right, an hourly revisit does not mean that you get an observation on the hour every hour, because it's not possible to design a constellation with orbital mechanics without vastly oversampling some region. So it is a global average. If you break it down by latitude, we're a little bit better than hourly in that the kind of 40 to 50 degree band. And again, near the poles, we have some longer gaps, about 60 degrees north and south and closer to the equator. So it is an average, but there are some longer gaps in there. I think that animation that I showed probably tells a story better than anything I can say here. So you do see some gaps there on the hourly basis, but when you combine what's available publicly with ours, I think the longest gaps are probably maybe there might be one that's in the 2 to 3 hour range, and most of them are under 2 hours.
I do see another question in the chat, and so I'm going to hop to that really quickly here. I asked a question about iMerge++. How would this differ from proprietary level 3? Sorry, I missed that.
So internally, we have the unified precip that I mentioned that goes out on our platform into customers. That's probably the closest thing to iMerge, but it does have some different requirements and limitations because we need data that's available with low latency to go into that. So we use our own sensors, of course. We use the geostationary satellites quite a bit, but we also use a handful of other missions. I think we use ATMS and GMI because those tend to be pretty reliably available with low latency, but we don't use some of the other sensors. So, iMerge has several different flavors, as like the early, the late, and the final. And so right now we don't do the akin to the late or the final. We essentially just do the early. So I think it would be great if and that might be a role for CSDA if this data does get onboarded to do an iMerge late or final using TMS data, to kind of fill in some of the gaps in the constellation.
Okay, well, thank you so much, Joe. Double checking here. It would be great if NASA could work on an enhanced iMerge. I agree with Joe. Thanks, Krista. Appreciate that feedback very much. All right, taking it. I was wondering if you had more thoughts about the kinds of problems that 3D ML tasks would have the most impact on for your data sets.
Yeah, this is a great question and very timely because it's something we're really diving into. I think that the 3D methods, in some ways, change what requirements might be. So I think they're great for trade studies, and if you're considering a new design like we are for Gen 2, we can. I'll just give an example for a sounder. If you're trading spatial resolution for instrument noise, so traditionally microwave sounders tended to be lower resolution because they were really driven by NWP requirements, which are very low noise measurements, and that means you need long integration times. And meanwhile, like the spatial resolution of weather models, and especially at the data assimilation scale, are in the tens of kilometers, if not larger. So they really don't have this requirement for really fine spatial resolution. And so all the designs, for ATMS have always been, to go towards these larger footprints, long integration times to beat down the noise. But there's other applications, like precipitation and tropical cyclone imagery, where you do want that high resolution but can afford some higher noise. And so why not design a sensor that, you sacrifice some noise to get that higher resolution? And then meanwhile, the 3D method can effectively learn how to do the averaging to still beat down the noise for the NWP application. So I really think it's helpful for these trade studies and learning about what sort of information is really in measurements in a holistic sense of the sensor, not just looking at a single footprint at a time.
All right. Well, thank you so much, Joe. Thanks to all of you for your contributions this afternoon and for the content. We appreciate you, everybody. With that, we'll leave the virtual meeting space opened, and we will log off from the audio component. So if you think of something you'd like to ask our presenters, feel free to type it in the chat, and I will forward those questions along to our vendor presenters as well as the program. All right, all. Take care now. We appreciate you. Have a wonderful rest of your morning, afternoon, or evening.
Thank you. And thank you so much, Jennifer.
You're quite welcome. Goodbye, everybody.